today, let's very quickly go through what did we do the last time. The last time, we looked at the origin of the exchange interaction. So if we have two spin bond halves, and they are residing on the atoms that are neighboring sites, there is some hopping between them. So there is a possibility if the spins are pointing in the opposite direction that one spin hops on the other one, then they interact, and then the same spin or the other one hops back, and it will result in a change of the spins. This can happen if they are in a spin singlet state, because in a spin triplet state, they can't hop onto each other. Okay, so these were where you like exchange coupling that leads to, that can even be like few thousand Kelvin. So next thing, I was starting to talk about cases where the material structure, where in experimentalists see that there is a finite ferromagnetic component of magnetization in some antiferromagnet. And then the question was, what is the origin of that uniform magnetization? And then Dzyaloshinskii came up with symmetry arguments. We looked at this particular case that we have a bond, there is a copper, and there is some oxygen that is not in the middle of the bond, but slightly off the distance here. And we consider the symmetries of this bond. It consists of the C2Y twofold rotation axis, and there are also two mirror planes that we can draw in this type of thing. And then we learn that if this is there, then something which looks like, and I hope this is again correct, S1 X, S2 Y minus S1 SY, S2 X may appear in the Hamiltonian. This expression is invariant under the action of these rules, how a different thing transform. Just remind me, X, Y, Z, they were so-called polar vectors. They are just like coordinates, and X tilde, Y tilde, Z tilde, they were the axial vectors, something that is kind of rotating, like a screw or whatever. And in that case, they can transform just like the regular vectors if they are really proper rotations. This maybe is the determinant one. Or they can add additional minus sign in the case that there is an improper rotation, like reflection or whatever, then the determinant of this 3x3 matrix, this transformation is -1. Then I started to introduce the microscopic origin. I was telling you that the spin-orbit coupling is eventually responsible for appearance of the anisotropies. That is that the spin starts to feel the environment, and there is some coupling between the spin space, as you do spin space, spin half with the environment. That this is the spin-orbit coupling. I showed you an example that there is a nucleus and there is an electron going around. Yes, please.
I have a question regarding the Hamiltonian. So basically here you have two terms, Heisenberg term plus BMI term.
That's right.
Does the sign of J and DZ matters? Like if the Heisenberg
it matters. It matters. There are situations that it matters. That's correct. So
like there's a ferromagnetic coupling in the Heisenberg term and the D is negative or positive.
It is more tricky. So for example, if you look at the firefly lattice is something that is made out of tetrahedra. So if you have a tetrahedron and you look at the symmetries of this tetrahedron, you will figure out that it's kind of similar to this situation, because you will have so you look at this point here. Hello. We are just recapitulating what we did the last time, so you didn't miss anything. So if you look at this bond, actually I think it has the C2 symmetry, rotation in this axis. Then there is also a sigma and 2 sigma. So actually this is the same situation that we had there. And then we can have a DM interaction in the direction of the C2 axis. So there will be a DM interaction that is pointing outwards. Now, this DM interaction will be pointing out. I mean, again, you need to have a convention for your enumerating your side. So this is 1, 2, and then outwards, and then you can take the CV rotations and other rotations to transform this DM to the other ones and the side indices and so on. And then you will end up with either positive or negative DM. And if you ask what is the ground state, for example, of this DM plus Heisenberg model for this tetrahedron, for different times of DM interactions, you will get different answers. In one case, the spin will point all out, and this is the so-called all in, all out. But in the other case, what will happen is that there will be, I forgot precisely, but there will be some ground state degeneracy. So it won't be uniquely determined. And that is a difference for the sign in this case. Symmetry doesn't tell us anything about the sign. It just tells us that it might be there. And if it tells you that it might be there, usually it is there. Right. Okay, so we were here. We have a nuclei, a strong charge. We are the electron. I'm sitting on the coordinate frame of the electron. And if I see that the charge is behaving as if it would have some velocity, and then it would generate some local magnetic field where I am, and this will interact with the spin 1/2 of the spin. So this electric field is the magnetic field was proportional to V plus E, whatever else, I don't know. Yes, please.
So I understood what you explained there, but from an intuitive perspective, the sign of dz should not affect that volume maximization.
That's correct.
So why does it make a difference?
Because here we don't care only about one bond, but we need to simultaneously optimize four spins.
Oh,
and we have 1, 2, 3, 4, 6 bonds.
Oh, okay. And because the dz is a vector, d is a vector, that's why it is probably making a difference. Like if there was a scalar coupling,
yes,
then if they're all same signs, whether they are same sign positive or negative shouldn't. Well, okay. Okay, but I got the point. Yeah.
What should I do?
No. I got the point.
Yeah. Right. Okay, good. So let's come back to this situation here. So, and we try to analyze this using the Hubbard model-like approach. We have electrons at home. So there is one electron from here, and it wants to go to this side. So, and there is this charge. So during the Hawking process, it will see this charge, and it will see this charge going in such a direction. It means that it will affect the spin of that particular moment, because if it is aligned with we will try to work it out. I mean, definitely it is nice to work in the frame where the spin axis is also parallel to B, because it's easier. So in this case, the B is in the direction of X, E is in the direction of Y, and B is in the direction of Z. Very good. Maybe not too bad. Maybe this was a lucky choice. So in this case, and I will delete the we don't need this anymore. So B Z is that what appears here. Okay. Side 1, side 2. So what would be the hopping? So B up, and you can have B down. Since the B and the up spin is also the z-axis. This is as the equal 1 up. Okay. So since this is diagonal in spin, we will have no spin flip there. And up, 1, 2, down, 1, 2. I'm going from 1 to 2, and then the charge is on my left, and then I will experience some BZ. So there is a T naught, that is say just T, that is the original T. Then there is an additional extra phase. We can think about this phase that, for example, the energy, I mean, there is a Zeeman coupling. So there is a, I mean, there is a sigma z is a coupling between the spins. This is like the energy. And if we have this energy, it would mean that if I propagate, I will pick up extra phase e2 energy times time or something like that. So there will be additional I times, I don't know, right here.
I mean, just, oh, because time is not clear what to be written.
Time is not clear. So this will be just phase. Let it. Right. So it will be modified and it will get a phase. For the downspins, I'm experiencing, I mean, this was up was positive energy, the down is negative energy. So it will be T times E2 minus I alpha. It will get a different sign. What happens if I'm coming backwards? If I'm coming backwards, T1, 2, up, then, I mean, I'm sitting here, then the charge is on my right.
You probably want to write T21 there, or?
I want to write T21.
Yeah.
Yes, it's right. I'm coming back, my charge is on my opposite side. So the B will be pointing in the opposite direction. So this will be T times E minus I alpha, and T to 1 down will be T to E I alpha. So this is how the presence of the charge will modify my couplings. I don't know how large alpha is, probably it's not too big. Okay, so let's see what happens with the effective exchange once these hoppings are here. So then I think I will delete this part here and remove this noise. So we have here, up, down, then and this is side 1, 2. We hope that up here. So we will have a situation where we have up, down, and this was T times E to I alpha. Okay, right here. Then I have a choice to continue and exchange the two springs. So the downspin can move here. If the downspin is moving here, downspin is moving from 2 to 1. It has the same I alpha, so there will be a T I alpha here. Okay, good. If I go back, then if upspin is going one direction, going back traces, there is T to I minus alpha. And similarly, there will be something like T to E minus I alpha. And then we need to consider also the other case. So it is going to be the energy axis this side. Again, the richer state here. We have the up down here. Okay, I was not careful about the Fermionic sign. If you do properly, there will be some minus signs because you have changed the fermions, but believe this is not important for this discussion. I mean, but if you want to do it carefully, you should do that down as well. Then what happens is that here it was the 2-1 that hopped, I mean the downspin 2-1 was hopping from side 2 to 1, and I think that corresponds to 1.
2-1 down. I alpha.
2,
I alpha.
2-1, 2-1 down in this direction. Sorry, in this direction. No. Yes.
Yeah.
What? Yes. Yes. This would be T times E I alpha. Is this correct?
Yes. So down hop from 2 to 1.
Okay. I hope and then we have e to minus alpha here, and then
Hi Ramal, I think there won't be time to discuss six-vertex model probably today.
my apologies. I was,
We are continuing, just in case.
what happened is that probably I thought that I can talk much faster last time, but I couldn't.
But you were around?
I'm around for some time.
Yeah, so if you want, you can one-on-one. Sure, sure. That sounds good.
So what we are doing is the introduction of, I mean, first, Heisenberg changed last time, and the Dzyaloshinskii interaction, and now we are trying to derive the Dzyaloshinskii
No
interaction from
problem. We
microscopic.
will talk to you about vertex model.
Okay.
So she's a high energy theorist.
Oh,
She's interested in not theoretic stuff. So that's why, and vertex model. So that's why.
That's the unmatched equation, Brady relation.
okay.
Anyway, we'll continue.
Okay, yes, right. So what we got is that there was this, if I know this dash and we got t to I alpha, and I think if we continue, probably that will be also t to I alpha here, and 3 times t to minus I alpha backwards. So what do we get?
Sorry, plus I alpha going backwards. Yeah.
Thank you. So we have effectively something that looks like a point that t up down state will go to down up with t square over u. T square is e to I alpha times t to I alpha. It will be t square e to 2I alpha divided by u square. And we pick up the same phase on this other part as well. So, and then we may ask what happens if we go in the other direction. So down, up, will go to up, down, with the phase no use t square into minus 2I alpha divided by u. Okay. So this is what changed. If we try to see how does it, I mean, we had our expression for the exchange interaction, and there was a sz term plus 1/2 s plus s minus plus s minus s plus. This was the case for the Heisenberg model. We need to modify this expression, namely, if and okay, there is also plus t squared over u, and I just come back. Okay. And again, I'm sorry, I don't know plus or minus. Right? So anyway, what matters is that here, so I had up, and this is 1 and 2, 1 and 2, 1 and 2. So if I had up, down, then acting with this term, I arrive to the up, down. Okay? No, this one. Yeah. So up, down, I act with the s minus s plus, arrive with down, up. I pick up an e to 2I alpha. So I should somehow smuggle in the e to 2 alpha term here. Similarly, in this other case, down up will go to I to minus 2I alpha. Up down, that is this term. And this term will get e to minus 2I alpha. Let me go rewrite it again. And I'm sorry for this. I didn't think in advance. I minus 2I alpha s1 plus s2 minus plus e to 2I alpha s1 minus s2 plus. Okay. Good. Now we can rewrite it into, I mean,
This one.
I delete this part here. So I think S plus is like Sx plus, I don't know, S plus is like Sx plus I Sy, S minus is like Sx minus I Sy, I think.
Yeah.
Then Sx is like S plus S minus, again, then it's factor here, it's 1/2. I don't know whether we put that
Right.
here or there. Sy is like half S plus minus S minus, and I think
I is in the denominator.
okay, right. So I can put here same side. Good. Very good. So we have those two guys. Then we can replace these guys. I know we need this one. So yeah, okay, right. So we need this one. So I'm replacing the S plus S minus into this expression here. So e2 minus 2I alpha S1 plus S2 minus will become e2 minus 2I alpha Sx 1 x to x plus I times S1 y s to x plus minus I times S1 x s to y and plus S1 y s to y. Okay, I'm just multiplying. Then we have the e2 2I alpha S1 minus S2 plus, I guess, it is e2 plus everywhere. E2 2I alpha, this will be the same, plus, here there will be a minus 5 S1 y S2 x plus 5 S1 S2 y plus S1 y S2 y. Okay, good. So if I add the two together, then I will get something that the cosine 2 alpha, and then I will pick up the the x and y term. S1 x, S2 x plus S1 y, S2 y, and we'll get a new term here. This will be plus S1 y, S2 x minus S1 x, S2 y here. And in front, I have the I times this minus I times this. So we have the I times e2 minus 2I alpha plus I times e2 2I alpha, and this is nothing else but sine 2 alpha. There are some factors of 2 that got disappeared, but what is important is that we have this cosine alpha, sine alpha, and then we recognize immediately that the dm interaction here is proportional to sine alpha. And in addition, the exchange path gets modified. It will become like, it gets modified by this cosine alpha, so it will be the j, it will be like,
Like Jz and this are not equal, is your
yes,
point?
yes, the z and the xy are not equal. Okay, and we can think about this as if we have just rotated the axis of the two spins. So we take, if you take one spin and you rotate your head a little bit, and then in this rotated frame, you can write down this guy. In other words, if I have only two sides, if I solve the problem will have the same spectrum as that of the original Heisenberg model. Just the wave function will be different. Okay, and this has been noticed in some works by, there were some, oh, I forgot the names, but it has been pointed out, like in 95, that people started again to look at the DM interactions they originate after the high DC. Okay, so if we have the same magnetic spectrum, why do we vary? Okay, so the one thing is that if we put a standard magnetic field, it matters how we choose the coordinates, so we can't really rotate the local coordinate axis. The second thing is if we have some more complicated passes, like the tetrahedron patch that we had there, then if I rotate, for one bond, I could rotate the axis, and then I know what happens. But then the problem is that if I continue, maybe we can't do that. And then there's a trouble, there's a frustration, so then the problem becomes more complicated. Good. So this is how the DM interaction arises from kind of microscopic principles. This is not what Moriya did. This is, I, I think this effect is called a Hungary effect. Like it is like when you put your charge into the solenoid, you have this Aharonov bomb effect. It's kind of similar, but much weaker. And right, I don't know if you would really. Shantika is not here today. She could tell you numbers, and maybe these numbers wouldn't give you the right values, or even maybe the other magnitudes might be off. But this is essentially the idea how this enters into play. So what we learned, how can we? There are these factors here. So how does the hopping look like? So the hopping look like is T. There is a T naught. Okay, these are the real and imaginary part. And we can write the hopping as this as I times sigma polymatic Z alpha mu that mu delta mu like this. And then the hopping Hamiltonian would be I hope this is safe to delete. Okay. Like the hopping Hamiltonian and the say minus 3 mu mu the side on 2 mu1 theta 2. I am not prepared. One and I'm in big trouble now. Either this or this. Sorry, I forgot. And I don't think that I can figure it right now. Okay, so it needs to be Hermetic conjugate. So like this, right? This is what you can say. Yes, very good. So we can write it, and this T mu is at this form. Right. So you may think that okay, so it doesn't really matter from where it is oxygen, where it is born. So the projection is that this T mu can be written as T some T naught delta mu. This is the usual hopping amplitude. Plus there's a part that comes from the relativistic effects, and that can be I sigma T right.
Yeah.
What?
TI or something.
I need one. I is not enough.
Okay.
I need a XYZ.
Oh, epsilon mu.
T. Yeah, eta. Let it be eta theta mu A, like this.
Sorry, what is eta?
Theta is x, y, z. These are the collimators. Sigma x, sigma y, sigma z.
Okay.
And then this will be because if we look in a different coordinate frame, then so this would be the hopping Hamiltonian for material where we have when we take into account this spin orbit coupling. The question is, can we determine from principle, from symmetry principle, what is the form of this hopping here? And this is why I left something here. And to get this, we need to know how C dagger transforms. We learned how the x, y, z polar coordinates and how the x tilde, y tilde, z tilde axial vectors transform under rotation, under specific elements of the symmetry group, but we don't know what to do with the C dagger. So this is what we are going to find out now. This is something new for me. So, I am maybe in a deep water, so well, I will try to do my best. Okay, so before that, I also would like to tell you something about the time reversal. How do we stand with the time?
11:06.
11:06. Okay, good.
And we can't reverse time here. And we can't reverse time here.
We can't reverse time. Yes, that's well. This is a different. I mean, this. Yeah, right. Okay, so let's don't open this. I understand that. Yes, we are getting older. So in this case, it was a dz that was finite. Time reversal. How to do time reversal? Yes, please.
So you started with Hubbard model.
Yes.
Then you derived the Heisenberg model, and how will BMI will come?
Yes.
And this hopping term is like for the Hubbard hopping, like the first term in the Hubbard model. So
Yes.
So this term corresponds to.
You mean this one? Yeah, right. Okay, yes. So there is the. I mean, I don't know if you. Okay, so yeah, we need to sum over ij and then sum. Okay, I can put ij here. Okay, right. Okay, let's stop here. Okay, so this is for side 1, 2, and there is the n up and 1 down. Yes. I don't know if this was the question you asked. So there is also this other kind.
And if we start like from situation when we are not at half filling, and like we instead.
Oh, it doesn't matter.
Okay, then we'll also have like.
Yes, you will have some DJ model. You will have even. I mean, I believe that this derivation of the hopping doesn't really.
Yeah.
I mean, it doesn't care about this thing here. That we cared about this because we are interested in Mott insulators. But even if you think, I mean, you have some heavy elements and you have some crystal symmetry, then the symmetry will still tell you that you will get these terms, and they may influence the band structure and so on. Yes, right. So she is doing this. I mean, like band semi-metals and all this stuff. That's all related to things like that. And maybe you may have situations that you have some closed loops and you go around the loops and then you pick up some phase and things like that. So this can give you like artificial magnetic field and right. Okay. So time reversal.
So one general question, Karlo, sort of from a research point of view. So all this sort of effects of symmetries on microscopic parameters, it has been sort of tabulated, or there are still open questions?
They are doing it.
They are doing it.
It depends what is your question. So DM interaction, how the DM interaction looks in different cases. I mean, first there was like one situation, but I mean there were like there is this quantum chemistry, whatever, then they go to, I mean, you have this database, they have the database, from there they extract the symmetries, and they construct all these things. So it is just tabulated. Now today.
Right. So I know that this stuff is tabulated and
Yes.
and like few things, but at the level of this
think
also more or less everything.
Probably yes.
Okay.
I mean, you see papers that they say that they include the magnetic space groups or double groups into the into the
okay.
into
Okay.
the
Got it.
you know the into this Bilbao.
Okay. Okay.
There is a site in Spain, the Bilbao crystallographic server, and then people use computers and so on, and they go to the space groups and the different positions, and you have atoms in different positions in the space groups, and then can all give you this. I mean, this is like machines.
Right.
Okay, good. Yes, time reversal. Yes, please.
Suppose there is O atom is not there, we just have a simple Heisenberg chain.
That's right.
And if we just apply magnetic field, so the chain is here, we apply magnetic field here. In that case also we can use this interaction. This chain.
Very good question. Very good question. So, yes, excellent question. So, what we have here, okay, right. So, what you are saying is that suppose that we apply the magnetic field in the z direction, then I lost some of the symmetries that I got. And then what will happen is that maybe P up will be different from P down. And this may already appear not as I, but as a real thing. So the question is that if we apply magnetic field, is it different from what we did here? And this is why I want to tell you about this being time reversal symmetry, because it will turn out that applying the magnetic field is making the time reversal. I mean, you don't have any more time reversal valid system, and in time reversal broken systems, then this may appear. But if you have time reversal symmetry, you can't have that. The real part must be equal, and you will have this I, but you are allowed to add it with an I. Right? So, time reversal, we learned that the Schrödinger equation or Hamilton or whatever equation of motion is something like this. So if we reverse the time, we put a minus sign here, then we can compensate by changing the I here. So if we reverse, and then we take the complex conjugate of the whole thing. So if we have some particle like a scalar that doesn't have any spin, then if we have some wave function psi, and if we reverse the time invariance, time reversal, then we just need to complex conjugate this thing, and I will maybe this will be my complex conjugation. So complex conjugation means time reversal for simple like spin zero particles. What happens if we have spin? So spin, we can think about is something that rotates. If we reverse the time, it will rotate in the opposite direction. So it is as if we would have applied the C2 rotation to the spin. So we rotate by pi the spin. Okay, so let's go slower. So this is my So this is my spin. It's not. This is the moment of the spin. It's pointing up. If I apply time reversal, it shall point down. This is the same as if I would have applied some C2 rotation to it around arbitrary axis. That is orthogonal to this basis right here. For convenience, I will take the y-axis. The y-axis, because the C2 y on spin 1/2 is proportional to e to I pi sy, which is equal to e to I pi half sigma y, and this, I hope this will be fine. So sigma y is complex. It is like 0, y, minus y. Okay, I don't know where the sign. So this will be like e to pi half.
We can use that Pauli identity.
Yes,
Right?
I would like to use something like that.
So it would be cosine pi by 2,
Which is 0.
plus I sigma y sine pi by 2 up to factors of half. Yeah, sine pi by 2, which is 1. Yeah, yeah.
Maybe this.
Yeah.
So that will be like 0, 1, minus 1, 0. Minus 1. Okay, it depends. Yeah. Okay, right. What it tells us that if we apply time reversal, then the upspin will become downspin, and the downspin will become minus upspin in the wave function. Weird. Okay, so time reversal for spin 1/2 up, I mean like C dagger up will become C dagger down, and C dagger down will become minus C dagger up. This is what time reversal does for spin 1/2 particles. There is this extra minus sign here that is kind of important, very important actually. Can we apply it to this situation here? So we have your reversible magnetic field. Let's try to figure out what happens there. So in the absence of magnetic field, what happens to this term here? So we would have C dagger up, C up, plus C dagger 1, 2.
Wow.
1 down. No, wait. C2 up, dagger C1 up, plus.
But what are we trying to do now?
I'm trying to figure out what terms are forbidden.
Oh,
You're right. Yeah, let's go lower. Let's go lower. Yeah. So we have this thing here. Let's apply the time reversal. This will become. Okay, actually, I mean this time won't be important here.
right.
It will be just C dagger 1 up, C2 up, and C dagger 1 down, C2 down. Will just become C2, C1 down,
Right.
down. So nothing really happens at the time reversal. Then can we have kind of
Spin flip hopping. Sorry.
why do they need to have the same? Why can't we have if we have time reversal, why can't we have different T up from different T down down?
No, I think the coefficients can be different.
No, they can't. Well, this is my problem.
Uh-huh.
That,
When time reversal is broken, right?
if it is not broken,
If it is not broken, they can't be
then
different. Uh-huh.
I need
I
something that is up is the same as down down. And
from this, it's not evident. Yeah.
from this, it is not evident.
Mhm.
And this is my problem.
I guess you need to.
And
Well, because you see, Karlo, C1 up, like the top left term transforms to the top bottom down. That's where it helps you.
oh, I made a mistake.
Yeah, we made a mistake. Correct.
Yes, thank you.
Yeah.
Yes.
Yes,
Very
yes,
good.
yes,
Very
yes,
good. Very
yes.
good.
Right.
Now,
Now we are good. Yeah, yeah, yeah.
thank you. Thank you. Excellent. Excellent. Yes. So you see that the sit up. Of course, you see. Now, thank you so much. Right. So this will go to this guy.
Right.
So and this goes to that guy. So
Right.
the T up needs to be equal to T down down.
Okay.
But there is also this conjugation I. So what you can say that is that if we have an I, then it will change to minus I, and then this term here will be allowed. Okay, just to tell you again. So if we have something like C dagger up like 1 plus I C up 1, 2, this time in the Hamiltonian, under time reversal, it will go to 1 minus I C 1 down, dagger C 2 down. And then is this minus I here appearing, and that will allow us to have this term in the Hamiltonian form, but even if we have a time reversal invariant system. And then you can play the game also for the other other spin hoppings that will not conserve the direction of the spin. My apologies. Is this okay? Good. No, I'm not saying that it's not okay. So fine. So the up and down spin they behave weird. Little bit weird. What happens if we here we have a C2 element, and this C2, if we apply once, and if we apply once more, then we come back to where we started from. What happens for the spin 1/2? If we rotate spin 1/2 by pi, and again by pi, and again by, then we will get a minus 1. And we need to rotate by 4 pi to go back. So that is something that is not included here. So we need to somehow to extend this group. I will tell you how. I don't fully understand how double, and this will lead to so-called double groups. I don't fully understand how it works. I will give you my interpretation that I start to somehow to how to rationalize what's going on. So I just leave this thing here. So what the C2 around, in this case we have the y-axis, then this is equal to E2 I we had it just a minute ago, sigma y, and this was equal I times sigma y. This is what is correct?
Yeah.
This will be 1 minus 1 1 0. We square this thing C2 times C2, then this will be equal to the mass 0 minus 1 1 0 0 minus 1 1 0. This will be minus 1. This will be 0 0. This will be minus 1. So C2 times C2 is equal to minus 1 0 0 minus 1. So this is like minus identity.
So just to clarify, we are working in the convention where sigma y is I minus I, right?
I don't know which convention we are working. So how is what is the sigma y?
The standard sigma is minus I.
Yeah, minus I?
Yeah.
Okay,
Yeah.
good. And if I rotate by, okay, good. Thank you. Then if this is the sigma y, then this is the, okay, fine, good. So we apply C2 two times, I get a -1. We apply C2, 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 then we will get minus C2, and C2 to the fourth power will be made 1.
Right.
So somehow, I want to take into account that they change my sign here. So I need to extend this row with a -1 element, that is C2 squared. And the -1 doesn't do anything to the x, y, z, and it doesn't do anything to those guys. It will, okay, and we need to figure out from the up, right, if I apply C2 to, this is the,
Right.
then if I have up, down basis, I apply 0, 1, -0, then I will get 1. I will get down and minus up.
Right.
Okay, so up goes to down, up goes to down, and down goes to minus up. Good. Then here, it means that up will go to minus up, and down will go to minus down. Okay? This is -1, and then we have this -1 times C2 minus C2 y, which is, I just copied these things here. And then I need to apply again. It will be minus down, minus up. I just I take this and then add the minus side. And
So the second one is plus up.
very good. Good. Now, it will also influence the sigmas here. So we need to figure out what is sigma xy minus sigma y z. And here I'm telling you what I'm unsure about and what I don't really understand. So I understand that the C2 is kind of rotation, and you can rotate, rotate, rotate. And then this is kind of natural to think as if you are in some, you extend your sphere or your rotation axis, and I don't know what the double cover is. So people say that the SU2 spin 1/2 is double cover of the O3. So you need to go twice to come back, and it's like covering the block sphere twice. I don't get it precisely. Especially, I mean, okay, with the C, I mean, if we have a CN, like 3, 4, 4, 4 rotations, we know how to work this out using the polymetric. But what happens if we have a sigma here? So sigma is something that is very discrete. You can't really make it continuous. It's something that you have this state and then you go over to the other one. So one way of out is that we can think about that maybe inversion doesn't do anything. And if we have a
Inversion doesn't do anything to the spin.
to the spin,
Its identity
yes,
in the spin space. Okay.
we assume that.
Okay.
If we assume that, then the C2 times, I mean C2y times a sigma that is orthogonal, I mean to the plane that is orthogonal to this y-axis, so that would be sigma xz, this inversion. So, and if I assume that this is 1, then I can tell that maybe the sigma xy is the same as the C2y.
Not inverse of that, but maybe inverse of that.
Oh, yes, inverse of that, but the question, yes, right? But then there is this minus thing, I mean this overall minus, and then, right. Or the other possibility is that that we look at the table of multiplication, and we have like, I mean, now we have more symmetry elements. C2 y sigma xy sigma zy minus. So this minus, I use this minus, but if you go to the literature, they may use some different object here that will denote that you doubled your group with this that element. Minus sigma y minus sigma xy minus sigma zy, and then you have here.
I see. So these are to be considered as different group operations.
Yes, these have to be considered different
because of that.
because I mean this is the same, but this part is different. On the spin bar up down.
Is this what is also called spin groups? Is this
No.
This is a different?
It is related to that, but
Okay.
it is not.
Okay.
The spin group they become very fashionable these days because of the antimagnets.
Right.
So what is the spin? Okay, so this is the magnetic crystallographic groups or double groups or whatever should be called. I don't know.
Yeah.
And they describe the material. I mean the transformation properties in magnets where your magnetization is tied to the lattice via the spin orbit coupling, for example. The spin groups they treat separately the spins and the lattice part. So you can have some, I mean like some symmetry operation here, but you say that it will not affect the electrons because you have a separate symmetry operation that will act on the electron spins, and you combine those two.
That is sort of more general than this. Like that includes double groups or no? Or they're sort of distinct? Okay. Okay.
I mean, there are many common things, but there are some subtle differences.
Okay. Okay. Fine.
I don't know the relationship who contains what.
Right. Fine.
But people say that if you have like parallel spins, then there is something that is new in the spin groups.
I see. Okay.
Right. Okay. So anyway, this is the table that we need to work out, and then we have the sigma xy, sigma zy, minus c2y, minus sigma xy, minus sigma zy. And but I just want to say that once we learn what to do here, then everything follows. That we don't need to think about some new element, because this is one, this is one, this is one, this is one.
with C2 should be minus 1. C2 with C2 should be minus 1.
My apologies.
Yeah.
C2 with C2 should be minus 1.
C2 with C2 should be.
I see. So in double groups, it is indeed minus 1.
Yes. I should put here minus 1, then I should put 1, and then I should put 1. Okay, this we know. Then.
So, okay, this is confusing. Yeah, this is confusing now.
This is confusing. This is very confusing now.
So maybe what we want to say, it's not minus 1, but because so
let's have here minus 1, minus C2. I think that was okay. I mean, this was
now it makes sense. Now it makes sense. Yes.
okay. Right. I go back. I don't know, to be honest.
No, but this is fine, right, Karlo? Because minus 1 is really not minus 1, but it is minus 1 in spin space, but 1 in space. So that's why they give a different symbol to that wherever else.
Yes.
Right.
Yes.
So it's sensible. Yeah.
It's probably sensible, but I'm not sure whether this is how they really define it.
Oh, okay. Okay.
Because they might define that the C2 times C2 is just 1, and then you have this extra thing here,
and then
extra thing down. So this is why
that's sensible. Yeah, I think.
So I mean,
I mean, I would do it like this. Yeah.
okay, check in the.
Hmm.
It's not easy to check because not many people. I mean,
So this is not part of the Bilbao server.
they are putting it this new, very new. So if you go there, okay, we'll give you the representation, and then there are some books that tell you how to do, like Desert House, and so it is in the books.
Okay, but it is not
I
in.
didn't do my homework.
That's fine.
Today.
But
I did half of my homework.
but it's not in Bradley Cracknell, for example. This time. The classic reference whenever they cite something like group stuff, it would be Bradley Cracknell, even for.
Okay, I don't know that.
Okay, so maybe this is not in there.
It might be. Yeah, I don't know.
Okay, in any case, please. Yeah.
Okay, so modulo, I mean, either we put here -1 here, and then we fill out this table, or maybe this is 1, and we need this extra 1 here, and then the table would somehow different. But nevertheless, what we have, we can have these matrices here, or what the spins do. And the trouble is that we need to find out what to put here for sigma xy, and then for sigma xy, we think that this is the same as the C to Z. Because if, let's assume that the inversion is doing nothing, again, you ask me that maybe we need to put the inverse of C to Z. Again, I don't know. So that would influence the sign here, the sign. And that would be like, for the up, we will, anyway, sigma xy is proportional to C to Z. Z is diagonal. So up will go to up, down will go to down. There will be some coefficients in the front. We just need to figure out what the coefficients are. So I think maybe an I and minus I can do it. Because if we repeat this 4 times, then we end up with the unity, right? So me and Z, right? And then once we have that, then we know everything, because from this we shall be able, I mean, these are the 2 by 2 matrix, and we just multiply those matrices, and we can fill out the other parts of this table. Okay, once we know this part, then just as we did for the time reversal part, we may try to figure out what is really allowed in that hopping Hamiltonian. And then we will get that maybe Tz or Tx or Ty or whatever are allowed if we have different, I mean, like the oxygen is not something like that, but maybe different direction and so on. So my apologies, I don't dare to try to do that part of, maybe you can do it as a homework, but I just wanted to transmit you the idea of these double groups, that the spin 1/2 objects are complicated, and they can play a game that makes your life more complicated and more interesting at the same time. But this is important for this, right? I mean, for all this topological stuff that is going on. Okay, good. Next. And you saw all the uncertainties that appears with these double groups. Thanks to this interaction, we look forward. So what happens here? What happens here? So we have a spin.
So, Karlo, just one general question. So, is this double group stuff, is it still a matter of discussion in the literature, or now it is sort of ready to go into textbooks?
I think it was ready to go into textbooks already, like.
Okay.
I mean, F electron system, people, F electrons, this is important to the F electrons. So whenever you see, like, they talk about like gamma 7 or gamma, I mean, they use this gamma whatever.
Okay.
Doublet,
this non-Kramer stuff.
Non-Kramers and Kramers and all this stuff. For the F, everything F, this is important. Okay. They know everything.
Okay.
Those people.
Okay.
But that tribe of people, and then we have other people who didn't even hear about
Okay.
F electrons, you know, and that's
Got it.
unique. I mean, this is well known, but not
Okay.
in the not in the general
Okay.
community,
Okay.
because there is no need for that in the d electrons or whatever.
So it's worth it to, I mean, this is a general comment again, worth it to write a textbook for condensed matter physicists, right? Like for in terms of group theory, not just group theory for physicists, but group theory for condensed matter physicists. Might be a worth it endeavor, right?
Yes,
Mhm.
I hear that. Yes, so there is certain knowledge that is scattered in different parts, and probably where we use together. Okay, so yes, what happens in this case? So we saw that there was an oxygen that's displaced, and then what happened is that there was this term appearing in the Hamiltonian. Right. Okay. Suppose we have a material, and suppose that we start from situation where we have oxygen in the middle. How can we enforce this oxygen to go away from the middle and to move up? What we can do is that we can apply electric field, and the electric field will move the oxygen that is 2- charge into one direction and the other guys in the other direction. Or in other words, if the oxygen is displaced, there will be an associated polarization in the y direction. Right. So this would tell us that here, instead of dz, we can write dz. We can ask if this expression here, so P is polarization, it transforms like a polar vector times s1x, s2y minus this. Is this invariant under this symmetry? And it will turn out that this is invariant. The displacement of this oxygen, if this is 0 here, in that case, it was there was no polarization because the symmetry was higher if it is in the middle, and there is a symmetry element that is not written here, that would cause this term to disappear. So as soon as this is off, then polarization is kind of linear with this displacement, so it will be kind of linear with the D.
Sorry, I just lost a little bit.
Yes.
So dz meaning it is pointing outside the plane, right?
So what happened here is that we arrived to the conclusion that we may have such a term.
Right.
Then this is just some number that we don't know, but then we add this z because it looks like that we have something like d dot s1 dot s2. Correct. And if we think about this trivial product, then this is naturally the dz. Right. So that's why it's got the dz, but yes, dz is kind of
Oh, dz is what you're calling pz. But
I mean, it appears that it transforms maybe similar.
No, the reason I'm asking is because in the diagram it is py. So that is different than pz.
Very good, very good, very good, very good, very good.
Like with respect to the diagram, B is outside the mode.
Okay, I am again in the shape. Sorry, I'm taking this.
Yeah.
Okay, so.
So now it's confusing, right?
Now it's confusing. So let's do it. We need to do it.
Okay.
We need to do it. So,
we put this in equation, right? How do you put py every time in that? Like how do you create polarization in this one direction by creating a simulator? So bonds could be like copper bond.
Yes.
So there is a copper bond over there as
Yeah,
well.
yeah.
And oxygen over there. So we have to make polarization along EY as well, like Z as well, EY as well, right?
Right. So I mean, what I meant is that suppose you have so like you have maybe relatives of the light on couple, and then this is the plane, and then you apply electric field along this way, and then it would mean that there will be some. This is making inversion symmetry, applying the electric field, and then some DM interactions will appear on all of these bonds. It is as if we would have pulled in this direction. Right.
But this possibility is not possible, right? That you have mentioned last class that one oxygen is the up, like upside the bond, and one is down, right? To contribute it, so it's copper.
Yes.
One oxygen is upward, one oxygen is downward. Yeah, that possibility.
Yeah, that you can't do it this way. I mean, this would be inherent to the crystal structure. So that
Not by doing external.
not by doing external. Yeah. So if you have an interface, I mean you have a 3D thing and you cut it on the surface of the cube, then this may happen. Because it breaks the surface of the cube breaks inversion symmetry, and then all these DM interactions or algebra or whatever, those can appear. And even today what they do is they cover it with electrodes, and they can induce these electric fields with electrodes in van der Waals like materials. Okay, but let's come to the problem. Let's to the problem. So what shall I write here? What is the polarization proportional to?
Right.
And then maybe I delete everything here, and we need to do it from scratch. Right. Okay. And this was done by Katsura Nagao-Sapalatsky in 2005, and they had some particular material. I mean, this was all driven by experiments, all this stuff. So experiments are important. Okay, so what we would like to know that, for example, how does S1 X, well, let's take it, S2 Z minus S1 Z S2 X transform. And here we don't need the double group, here we need just what we had last time. So if we apply the C to Y, it will change the sign of the X and Z. So this is doing nothing. This will be, okay, the C2 will just leave it as is. But we need to change the 1 and 2. So there will be minus S1 X to Z plus S1 Z S2 X.
Sign change.
So it got a sign change. So this is not invariant. But if we look here, the X and Z, they also get a sign change. So if I multiply this thing with X, or if I multiply this by Z, then this thing will be invariant. Right. So then we may start to have this type of case. Let's go to the next one. Sigma xy. The sigma xy, what is it doing? It will change the sign of sigma xy. Sigma xy is here. It doesn't change the 1 and 2 sign, but it will change the x and y. It will change the x and y. So, S1 x S2 z minus S1 z S2 x under sigma xy will become minus S1 x S to Z plus S by Z S to X. It gets this sign because we have the X there. Z also changes sign. So if I write here Z, this will be okay because Z also changes sign. Good. So this is invariant. X is not invariant. It's only invariant under C2 and the sigma X pi kills this there. So this one is allowed in the Hamiltonian. And my apologies, you were right that this yes, I was thinking too quick to write this, but this is the form that will enter like in the Hamiltonian with the B.
So that implies that the polarization has to be in the Z direction, right?
Yes, in the Z direction. If that I am again in a trouble because I thought that this would be the natural that I can put here dz instead of dz. We need to, but there must be a part. Okay, there must be something we divide. And then we need to figure out, okay, so this must be the Z, and maybe there is a spin,
okay,
like
which was disallowed last time, but now it gets allowed.
Yes,
I see.
It gets allowed.
I see.
Yes.
And
then we get this term.
I see. So that would be the magnetoelectric coupling.
Both are this and this are both magnetoelectric couplings.
If there's some polarization in Z direction also, it will work. Yes.
Right. So, and then I mentioned there was a question last time that that if you have a linear chain, how can you have a spiral state? One possibility is to have a DM interaction. The other possibility is that you have a frustration, so that you have like a J1 and second neighbor J2, and if J2, the second neighbor interaction is Sonia, in that case, you will have a situation. So this is your chain, and you have like this is your second neighbor J2. This is your first neighbor J1. You recognize that these are like kind of triangles, and then the ground state can be something like this, and then you need to continue, and so on. It can be anywhere. The plane can be anywhere, any direction, because this is the Heisenberg coupling. But when there is a spin-orbit coupling, in that case, polarization can appear that is related to the direction and the nature this spin spiral appears. So, and then this has been measured, and so there are materials, and that's why they look at this effect. There are other possibilities as well. So, for example, I delete this now here.
So, Karlo, just to make it clarify, so DM interaction is a certain interaction.
Yes.
And the magnetoelectric coupling is a different interaction.
It's a different interaction. Yeah, that's correct. They both, this type of magnetoelectric coupling, they both originate in the spin orbit. They are both relativistic effects. You may have magnetoelectric coupling that is not like this, that comes from, like you have triangles, and then maybe right. I will also tell you that.
Okay.
Suppose we have a different situation. Suppose we have this is a tetrahedron that is seen from above. Okay? And in the center of the tetrahedron, or maybe like this, and then I need to so this is a tetrahedron. Okay, so we started. and there is something in the middle, right? So can we have, and this is a so-called non-central symmetric point. Non-central symmetric would mean that there is inversion symmetry. In this case, there is no inversion symmetry. It's not like, okay, I don't this is what I have. So usually we have something like, can we have a, and we have time reversal invariance. So can we have a coupling like this? If there is a time reversal, okay, we can have situations like this, P S square, P square, S square. So inversion will change the sign of the P, it will become PS. So this is, if we have inversion symmetry, this is not allowed. If we have time reversal in the system, then it also changes sign. So this is also not allowed. Inversion allows this term, and it is the time reversal that kills this.
Sorry, what is P and S? What is P and S?
P are just some polarization, and this is some spin.
Vectors.
Kind of vector. Okay, so what I mean some combination of P and S.
Okay.
And the inversion will change the sign, and the time reversal changes the sign of S. So if we have a system that respects time reversal symmetry, then this is the type of term that can appear. So we have like P and 2S even, and this is what happened here. That I just deleted. There was like a EY, and there was a SX. Well, I forgot what it was. Minus something. You know that there was one P and 2 S's. So these are kind of the terms that are allowed, and polarization can be linear in the cases where there is no inversion symmetry. Here. So this is non-central symmetric, that's why we look at the line those. Right. So in this non-central symmetric, I'm introducing the notion non-central symmetric because you can hear it many times. So in the non-central symmetric situation, we can do the same thing, and we arrive again. You can write up those things. We will have like a C3 rotation, and we will have some C2 rotation like that, and we have some sigma planes. Eventually, you will end up that in the Hamiltonian, you can have something like Px, Sy, Sz plus Py, Sx, Sz plus Pz, Sx, Sy. Okay. This is the spin in the center. Now, if you have spin 1/2, you can't have this term, but if you have a larger spin, you can. So, for example, if you have a spin 1 or spin 3/2, then you are allowed to have such a term, and then suppose that you have your spin that is pointing in the direction of parallel to the lower path. It means that it has components that is S F, S, X, X, Y are finite, then a Z polarization may appear, and I will show the polarization with this yellow. So then we will have a Z, Z appearing in the system. And this is the magnetic moment. There is a material that has this tetrahedra in its structure. It looks as follows. So it is a material where it's a square lattice, and it has this tetrahedra, and these tetrahedra are not uniformly distributed, so not like this. And there's a slight tilt. So I will try to draw the yellow tetrahedra here, like this, like this. And then the same here. Something like that. That's like A and B. And it has cobalt atoms in the middle. and this is antiferromagnet. So below the near temperature, there will be some magnetic moments that will be like that. Okay. Now, if you apply magnetic field, external magnetic field, then what happens is that if these are antiferromagnets, they will, in external field, the antiferromagnets want to tend. So what happens is that if they rotate freely in this plane, if we apply magnetic field, we can select the direction of the antiferromagnetic moment. And if we rotate the magnetic field outside, these antiferromagnetic moments, they will follow the field as we go around. And then we can measure the polarization along the z-axis. And once they did this experiment, what they found is that there is a polarization that is kind of behaving like this. And
this is the angle with respect to the angle.
This is the angle here, and this is the 2 pi angle. This is the pi angle, and this is the sharp zero. So they rotated once and once again, and if you rotate one cycle, you get 2 cycles of polarization, and that is related to the fact that what you have here, you have the S 2 times S, and you put here the E phi, then there will be a 2 I phi appearing in the field. So they can observe this. Okay. So there is some polarization happening here. How can we think about it? I mean, that is nuclei. It is not the cage. I mean, cage is rather rigid. It is rather the distribution of electrons in the nuclei that kind of moves up and down. And one can work out microscopically from the spin orbit coupling how this happens in this case. In this crystal field thing. I haven't done it. Some people did it. Arima Takai-san, a Japanese guy, I mean professor, he derived this. And again, there was this material that simulating his work. This thing here is actually something that is called the spin quadrupole. Here earlier, when we were discussing about this physics, it was like polarization and 1, 2, 1, 2. So this was an object that was living on 2 different sides, and this can also exist for spin 1/2. So here we need 2 sides, and there was an antisymmetric combination of those 2 spin 1/2. So nevertheless, this is not a quadrupole, this will be just a dipole. Spin dipole. It will have a total kind of spin 1. This guy is different. This is something that is like behaving like spin 2 object. Okay, right.
So this happens for spin 3/2, for example.
So spin 3/2 or spin 1 or any larger spin, if you have some material in your lab which has this non-center symmetry. I mean, this is still quite symmetric. There are more ugly materials where the symmetry is even lower, and then there's a mess. Now, what can these materials do?
Sorry, just to understand. So because we only relied on the point group operations, therefore it is also applicable for spin 1. Anytime time reversal will be needed is in.
It depends what. So
no,
here we have S and T operators.
Mm.
They don't involve the C dagger directly.
Right,
They
I understand.
involve the C dagger square.
Then we just need the actual time reversal on spin.
We don't. And they are on all the extreme side.
Yeah.
But once we were looking at hopping amplitude,
Got it.
then you had the.
Got it.
Right, then we need the double. Or if you want to figure out what are really allowed, for example, you want to look at the superconductivity, and you want to find out what C dagger pairing amplitude or other parameters allowed, then you need to go to
Got it. Right. Yeah, just for spins we don't need this stuff.
For this type of considerations, you
yeah.
Now, right here.
Right.
Yes. Okay, so what are the consequences? So usually, let's say we have some spin material, some magnet, and then we want to see what experimental probe can interact with the spins. There is a Newton scattering, and if a Newton scattering comes in, then it will interact with the spin or with the magnetic moments via the dipole-dipole magnetic interaction, and then there will be scattering. Another probe is the light. The light has two components. The light has an electric and a magnetic component. Magnetic component will interact with the spin, and the electric component may interact with the polarization that is induced. So it may happen that the light, this is the propagation of light, and then you will have like, this is the usual picture. So this would be, say, the magnetic component, and then on this line your choke, then you have a corresponding electric component. And depending on the direction of light propagation, you have this rule of the right hand, then propagation of light and E and B. And if you go in the other direction, then say if you keep the B the same, then the electric field will be
So Karlo, just to say that I think we are probably reaching saturation.
We are reaching saturation.
So,
this is the last thing.
Okay, perfect.
Right, yes. So if such a light propagates in a system where you have both polarization and spin, magnetic moment, it may happen that depending on the direction, suppose you have this that S pointing here, P is pointing there, the light propagates and it will interact, the electric field and B will interact with these guys here, and in one case, it will be positive interference, meaning that it will be enhanced. In the other way, it will be just reduced, one of the components. So the light will propagate easier or more difficult in such situations. And then it may happen that you will have a sample and you shine light one way or you shine backwards, and then you will have a different absorption of light. It's like a diode. Or what you can do is that you reverse your external magnetic field, and again you can achieve this. This is called non-reciprocal diquasar. And you can, once you have this polarization spin parts in Hamiltonian, then there will be many, many effects when you describe interaction of light and matter. Okay, I think you must be hungry, you must be tired. I'm tired. I'm half prepared. I'm sorry for that.
No, it was perfect.
And thank you very much for your attention. I'm sorry that I didn't talk about topic 2.
It's okay.
Currently,
there will always be a next time. No. That only invites a next time. Yeah.
Yes.
So let's give a big round of applause to Karlo. Thanks a lot.